to the cloud. It says it's recording, right? So I'm going to take that to mean that it's actually recording. Like, why is he talking like this? Well, last night I taught a pre-calc class, whole lesson, 2 hours. I waited for the file to appear at the end after I signed off, which it always does, and it just didn't. Okay? So I'm very nervous. I'm gonna hope that this plays out the right way. Otherwise, I'm gonna not be a happy camper, and I can't imagine other people will be either. All right. So oscillating discontinuities. These are the most difficult to define, as they're simply functions which oscillate around a point too much to have a limit at that point. All right. So here's an example: y equals the sine of 1 over x. So I'll just type that in: y equals the sine under trig of 1 over x. And in Desmos, it looks lovely, but what is really happening here is, because it looks like you're getting a lot of coordinates along the way, but what's happening is, as you zoom in, as you bring it in closer and closer, if it'll let you, if I can actually get my fat fingers to navigate this whole thing. Well, now it thinks I'm trying to like hit the curve, but bottom line is, there's so much of I'm trying to get it to not register. Okay, there we go. There's so much going on at that point of oscillation that it's too tough to tell what the y value is at that x value of specifically 0 in this case, right? Because that 1 over x gives us a point that's undefined. So if it's undefined as a composite function, so part, the interior of another function, then it's going to be the whole function is going to be undefined, right? But we can bring it in, or at least try to bring it in more, by making our minimum x value, the smallest value of x, make it something really close to 0, but on the negative side, so I'll say 0.0001. And then on the positive side, we'll say positive 0.00, oops, got a double decimal there, 0.0001. And then as far as the y values are concerned, you can kind of go with whatever you want there. So I'm going to say like -3 to 3. And then tap out just to give some wiggle room. So this is what this graph is showing. It's essentially saying that there's so much oscillation going on. It actually becomes more and more of an oscillation the closer you get to 0, that it's essentially an indeterminate situation. You can't find the limit at that location. All right. So let me bring it up on the TI calculator and show you the difference. So let me clear this stuff out. We're looking at the sine of 1 over x. When you do it on a TI, you're kind of at the mercy of what's available in terms of window settings. So I'll just start off with a window of, well, -512 isn't going to cut it. I'll say -1 to 1. And then my y values, I'll just keep that at -3 to 3 like I did for the other for Desmos. And then take a look at the graph. And so this is what's going on the TI. All right, but you can see here, I mean, it's still a pinch zoom type of situation, but the more you zoom in, the less clear the situation is. Like what's going on here, we can't really tell. Eventually, till it gets to a point where it's like, all right, we know that there's a big black blob in that display. We just don't know what it represents. All right, so we would need another method to find the y value corresponding with a particular x value, because this isn't going to cut it. All right, so that's an oscillating discontinuity. We say a function is discontinuous at that point of obviously discontinuity, but it's in an oscillating fashion. All right, so we're going to come back to that when we talk about particular cases involving limits, but for now, we're just going to kind of switch gears and talk about the way graphs behave So one way to determine the behavior of the graph is to determine things like domain and range, where the function increases, decreases, and all that good stuff. All right. So these are really the key ingredients of identifying how a graph behaves over an interval. Right. So what we're going to do is, well, I'm going to mark these graphs up and show you the bits and pieces. So domain are the possible values of x. Right. So if I look at the values of x here, I can see, well, the x-axis extends from negative infinity to infinity. So I would just trace along this graph, and make this thick. I would trace along this graph from negative infinity. So that arrow symbolizes the theoretical event that I get to negative infinity in terms of x, which is to the left. All right. The fact that the graph is pointing up is irrelevant. We're talking about just the x values. All right. So horizontal movement along the graph. All right. So every point in space can be manipulated in a horizontal fashion. Let me thin that out actually. So it could go left or right, or it can go up and down. What we're focusing on is the left-right aspect of it. All right. So this graph is moving to the right. Right. Our choices are left or right. Yeah, it's also going down, but it's still going to the right, down and to the right. All right. Didn't do that on purpose. All right. So as I continue following along this graph, I'm still going to the right. So I'm not going to the left, I'm going to the right. All right. Continuing on, still going to the right until I get to a positive infinity. There were no breaks along the way. This graph started at negative infinity and ends at positive infinity with no interruptions. So that means the domain is going to be an interval notation, negative infinity to infinity. All right. Now, in terms of the range, for the range, we're concerned about y values. So it's an up and down situation. All right. So our possibilities are either up or down. All right. Now it's going to depend on where we are in the graph, whether we're going up or down. So if I start off at negative infinity for x, I'd also be starting off at positive infinity for y, because this graph extends onward in the upward direction, onward and upward. All right. So positive infinity is over here. Lord only knows why I wrote a negative infinity over here. I apologize. That should have been positive. Positive infinity is to the right for x and up for y. Negative infinity is to the left for x and down for y. All right. So this graph is starting off at positive infinity somewhere, and then we're going to decrease. All right. So we're going down. All right. On this interval, we're going down from left to right. So the question is, will I always be going down? Well, no, because once I get to this location, go green. Once I get to this location over here, I'm now going to be going up. All right, so I'm going up over this interval. So down for that first interval, up for the second interval, then down again for the third interval, that third little piece here, and then up again until we get to positive infinity. I know it's kind of hidden there, but until we get to positive infinity, we're going to be going up. So if we can't ever get to positive infinity, we're always going to be going up as we go to the right. All right. So what does that all mean? Well, in terms of the range, we're looking for the lowest and highest possible values of y. All right. So along the way, as you're tracing out this curve, you're starting on the left, you're tracing out the curve. Eventually, you'll get to the lowest point. then you'll get to a what we call a relative maximum. It's higher than the points around it, but it's not the highest point overall. And then you can follow the curve forever, right? In either direction. If you want to go to the left, you can go to the left. But there will be a defined minimum value, right? So that would be this location. I'm going to go purple for those people who are home. That's this location here. This is the minimum of the graph. All right. That minimum has a y value of 1, 2, 3, 4, 5, 6 units below the x-axis. So the lowest point on the graph will be -6. Now the graph will go up forever. Whether you go to the left or to the right, the behavior of the graph is to increase without bound. So it would go up to infinity. Now for increasing, decreasing, and constant, increasing is a part of the graph, C, D, E, and F. A part of the graph that has a positive slope. Decreasing is negative slope. Constant would be a 0 slope. And then discontinuity is a separate idea. All right, we'll get to that in a minute. So if a graph is going to have a positive slope, that means it's going to be going uphill as you move along the graph from left to right. Okay, so we're talking about all the instances in which the graph is going uphill. That would be this region here and this region here. Those would be increasing. So going from this location that got big. Going from this location and then increasing until we get to the highest point on that interval, all of these points would be part of the graph that's increasing. All right. So we would just state the x values for which the graph has a positive slope. All right. So that's going from go with a light blue now. So that's going to go from this point here along this x value to this x value, right, to the peak of that graph. So you just got to count boxes. It's going from -5 to -2. There's solid points at those locations. There's no open circles or breaks in the graph or anything. So they would be square brackets. All right. But we also have another interval for which the graph is increasing. All right. So that would be this piece. Same idea. We're going uphill. Reading the graph from left to right, we show an interval in which it's going upward. All right. That's the positive slope. That happens from this x value here on and on forever. It never stops, right? That x value has a, or that x is a value of 1, solid point, but then it never stops increasing after that. All right, we're going to unite these two sets, and that would be our union. All right, I'll get you, Cameron. I'll get you. So downhill would be pretty much everything else, because I can trace it out. The diagram's getting a little messy here, but if I just kind of put this in motion, starting here and working our way to this point, we see that the graph is going down from left to right. Starting here and working our way to this point, you see the graph is going down from left to right. All right, so that would be those two intervals. So we just got to name them. Well, this x interval corresponding with this piece would start off at -infinity in terms of x, and then it would stop at this location here, which we said before is -5. Then we'd be looking at this interval here, another piece where it goes downhill, which starts off at -2 and ends at +1. So -2 to 1. Now we've accounted for every part of the graph. There's nothing that's been left out. So we know that there would be no interval for which the function is constant because there's no interval left. We've covered everything from negative infinity to infinity. Also, if we're talking about zero slope, we're talking about a horizontal line. All right, I don't see any horizontal lines. So this would be none or no solution, empty set, whatever. Points of discontinuity. Well, any break in the graph. I don't see any break in the graph, so we're good there. But even if I did, I'd still have to start thinking about what kind of discontinuity it is and where it would be located. All right, but in this case, it's irrelevant. We have no points of discontinuity. All right, there's no removable discontinuities. There's no asymptotes, infinite discontinuities. There's no oscillating discontinuities, no jumps. So that would be it for this.
Professor, I have a quick question for you.
Sure.
As we go past the, in this case, the minimum at -5, I guess, is that slope not 0 at -5?
That would be an instantaneous slope. We're talking
Right.
about average slopes.
Okay, understood.
So over an interval.
Okay.
So for the next one, domain and range. I'm going to just copy this stuff so I don't have to write it again. Domain and range, we're thinking about where the graph starts, where it stops. So, you know, I mean, I went a little crazy with the markings here, but it was just trying to get the points across, literally and figuratively. So 1, 2, 3, 4, 5 units to the left, so -5. That's the beginning of my graph. All right. If I create, I'll create a point just to have something to drag across. But if I start here and work my way to the right, I'd eventually get to this open circle, a non-existent X point for this piece. But it is in existence for X for this piece. All right. So 1 would be excluded. The X value of 1 would be excluded for this piece, but we would pick it up from this piece. All right. And then continue on our way out to positive infinity if we can go on forever. All right. So I could say one of two things. I could say that this graph starts at -5. Ooh, that's -5. Solid point there. Goes until it gets to a +1, but does not include that 1. That open circle tells us that we don't include that 1. But then for the next piece, we would start at 1 and go to 3. Solid point at 3, so we would include that. And then that last piece, this one over here, that would start at 3 and go to infinity. All right, so that's one possible way of writing it. But if you think about it a little bit more intuitively, you would start asking yourself, well, do I have to write all those pieces? Well, the answer is no, because if you go from -5 to 1, but don't include the 1, and then you go from 1 to 3, including the 1, now 1 is part of your set. We're not skipping over any values of X from -5 on the way to infinity. So we could say -5 to infinity because every single X value in that interval from -5 to infinity is included. All right. Yeah, there's a discontinuity along the way, but we'll address that later. All right. The range is talking about the lowest value of Y and the highest value of Y. All right. And any intervals along the way. So you could have a break in the graph in terms of Y, but if you're careful and you just take, you really think about what you're doing, it should be easy to pick up on. So if I take my point, start off over here, I'm at 1, 2, 3, 4, 5 units above the X-axis, all right? So that's at a Y value of 5. I'm decreasing, approaching a Y value of 4, but I never get there, all right, for this piece. But for this piece, I actually do get to a 4. So 4 is still included in the set. then I'm going to get all the points between 4 and 1. So really that's telling me that my range ought to be 1 to 5. All right, because we're not skipping anything between 1 and 5. We're getting every one of those y values between 1 and 5. All right, they're all accounted for along the way. The positive slope, I'll use a highlighter this time, hopefully make it a little less noisy. Positive slope, negative slope, and this time we have constant slope. So positive, negative, so increasing, decreasing, constant. All right. So I just want to be thinking about the x values for which the graph is increasing. It seems to happen between 1 and 3. The x values for which the graph is decreasing, that seems to happen between -5 and 1. But open circle on the 1, that's going to be a closed paren. All right. So even though 1 is part of the domain, it's not part of the piece of the graph that's decreasing. So it would be excluded. All right. And then the constant starts off and starts being constant at 3. It simultaneously stops increasing and starts being constant at 3, but then never stops being constant after that. It plateaus. Now, in terms of stating points of discontinuity, we don't have to state y values, we just have to state x values. And in fact, y values could be infinite. Like, for example, if there's a vertical asymptote, it's a discontinuity. It's like, okay, well, what am I going to say the y value is there? It's infinite, right? So we just state the x value for where the break in the graph occurs. That x value is 1. Right? Because it's right here where the break in the graph occurs. Okay. So let me stop that recording. Are you sure you want to stop recording to the cloud? You'll receive an email notification when the cloud recording is ready. Yeah, that's